looking at the generalized pigeonhole principle this time, and basically we're going to start with an example and then we'll show the theorem. And let's suppose we've got 13 pigeons. They're placed into 4 holes, so basically, they're going into all of the holes. Of course, we can see that 13 is not divisible by 4, so there's going to be a hole of at least 2 pigeons if they have to go into the 4 holes. Okay, so no empty holes. So they're placed in some way into 4 holes, and there is some hole that's got to have, we've got to show there's got to be a hole that's got at least 2 in there. Well, it's pretty easy to see that because, as I said, because of divisibility, there's going to have to be at least 2 in one of the holes, because even if you put the same number in, or I should say the minimum number in a hole, which is 1, you find that you've got to put obviously more than 2 in the other. So something like 1, 1, 1, that's the minimum number, but you'd have to cram 10 into that one. So obviously, yes, that's a pretty easy one to see. In fact, a hole must contain at least 4, because again, if you put the minimum number in one of them, you got to do various scenarios, like possibly this one, or let's keep the minimum here, and you'd have to do something like this here. So there's various scenarios, and you can see that if you try and keep it underneath 4, it's not possible for all the holes. So I could go on. So it's pretty clear to demonstrate this to yourself. In general, if we have at least m times n plus 1 objects placed into n holes, then some hole will contain at least m plus 1 objects, which is the generalized pigeonhole principle. We can see for the example above there that if we had 12 pigeons, 1 fewer, that have all got to go into a hole, you've got 3, so the 13th, 3 in each. Even if you wanted to try and dodge it under 4 from above, and basically the 13th's got to go somewhere, so it's going to, whichever one it goes into, it's going to bump that into 4. So let's look at those numbers that we, in terms of the theorem, the numbers that we used in the example up there. We've got something times something plus 1, so we've got 13 equals mn plus 1, so 12 is mn. Now n holes, well, we've got 4, so alright, so obviously m equals 3, and therefore m plus 1 objects would be 4. M plus 1's 4. Okay, so we've got 16 natural numbers in the next example, and we're excluding 0 from our count of natural numbers. 16 of them, and they're written down and prove that at least 4 will leave the same remainder when divided by 5. So 4 of them will leave the same remainder. So what we can do for our so-called holes is to look at the remainders that are possible when dividing by 5, and there's 0 through to 4. Okay, and so we would have 16 equals mn plus 1, so 15 is mn, and therefore n is 5, because we're looking at being divided by 5, and that would make m equal to 3. So that means we've got m plus 1 according to the generalized pigeonhole principle of at least. So m plus 1 is at least 4. So we have Therefore that means we've got at least 4 objects there. In the final example, this is like pigeons in multiple holes, you could say. Needs a little bit of explaining. So we've got 7 people sit around a table of 10 chairs, and basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and whoops, there we go, a little bit bigger there. 8, 9, 10. Just tidy that up a little bit there. Alright, and so we've got to show that 3 chairs at least, so show that there are 3 consecutive chairs that must be occupied no matter what. One way of doing it is to consider 1, 2, 3, 4, numbering all the seats around there from 1 to 10, and then all of the groups of consecutive chairs would be listed like such. Now you'll find there are 10 of them when you go through, right through the last one, and really you can see why that is, because all you do is just change the starting one, and we reconfigure the problem. Each of the 7 people will actually belong to these groups on 3 occasions. So if we look at 1, for example, it'll belong there, there, and there. Okay, so it's a bit like having 21 people allocated to 10 groups, and basically using the pigeonhole principle we can see through that that we've got, if I write it down on the side, on the right hand side here, 21 equals mn plus 1, 21 equals 10 m plus 1, that's an m, 20 is 10 m, m equals 2, so m plus 1 is 3. So we've shown what's been required.